Welcome to Three Devs and a Maybe, the podcast series for beginner web developers and general web enthusiasts. Now, introducing your show hosts, Michael Budd, Fraser Hart, Lewis Caines, and Ed Mann.
Hello and welcome to another episode of Three Devs and a Maybe. My name's Ed Mann, and today we're very lucky to be joined by Mr. Michael Budd. How you doing, Mickey?
I'm good, thank you. Good to be here.
And Bruce Momjian. How you doing, Bruce?
Good. It's been a little crazy week, but I always enjoy these interviews, and I've been traveling like crazy this year. I think since January I've been to 15 cities.
Wow.
From Singapore to Siberia. So I'm very happy to doing something that is local today. So
yeah. Local, but via the internet. The beauty of the internet, you can be anywhere and everywhere. Oh, that's awesome, man. Yeah. I mean, would you mind just introducing yourself to the audience?
Yeah, sure. My name is Bruce Momjian. I live in Philadelphia. I've been working with Postgres since 1996. Before that, I was an application developer. Before that, I was a high school teacher. And I've been working for Enterprise DB for 10 years. And they specialize in enterprise tooling for Postgres. And my primary job there is to help to develop the community and keep the community running smoothly and help out where I can. Of course, I attend about 30 to 35 conferences a year. And I do these kind of interviews. I do webcasts. I occasionally visit customers. And I work from home. So I've been doing it for a long time now, probably full-time with Postgres. I've probably been 17 or 16 years now. And it's really a great job. I love it.
And how did you get interested in that database systems then?
You know, it's funny. I've always been drawn to it in an odd, illogical way. I don't know how to explain it. But when I was a high school teacher, it was primarily I was teaching Pascal and trying to think what other languages, mostly Pascal in the academics. And when I became a database consultant for law firms in the 1990s, I used a lot of relational databases, including Informix and Ingress. And I was always fascinated about how these databases could take what looks like English, which is what SQL appears to be, and sort of interpret it into a language that it could understand and optimize and then return the results as quickly as possible. And I was always fascinated about, like, how does that work? How does it know what a keyword is? How does it know how to parse things? And I started to get really interested in it. So I actually wrote my own little database in shell script. It was actually posted on Usenet. It's still around. It's called SHQL, and it actually works, but it was kind of a conglomeration of awk and grep and shell script. Then I tried a version in C, and then in, I guess, 1996, I was running Unix at home. And I was like, I'd really love to run a database at home. And at that point, as you know, databases were hugely expensive. And I tried MSQL, which is out of actually Australia at that time. And then I eventually found Postgres, realized it was really interesting software, but it was very buggy. And nobody's really like organizing it. So it had a lot of potential, but nobody was really kind of helping to take the patches and make releases out of it and sort of develop a process to improve the software. And that's how I got involved in the spring of 1996. And for about 3 years, I worked as a volunteer while I was still obviously doing database consulting on an hourly basis. And, my wife would kind of say, why are you spending so much time with this Postgres thing? And, I was paid hourly, so she knew when I didn't work a lot in a month. And I said, well, we had a big release that month. And, I had to, and she's like, well, why don't you spend more time with the family instead of doing that? Of course, there's no answer to that question.
Yeah, you can't win. You can't win with that.
You can't win. You just don't even, you're just like, you just got to give the deer in the headlights look at that. But actually, one time I helped somebody on a Saturday. It was flowers.com. And the doorbell rings on Monday, and it's flowers. And my wife's like, hey, where'd these flowers come from? I'm like, well, that Postgres phone call I took on Saturday, that was flowers.com, and they sent me flowers. And she's like, oh, you should take more calls like that, And then I was asked to write a book about Postgres by Addison Leslie. And in 1999, I'm always like, well, okay, now he'll be an author. That's kind of cool. And then things pretty much took off from there. I worked for a Postgres support company out of Norfolk, Virginia in 2000, 2001. Then I worked for a Japanese Postgres support company for 5 years called SRA. And then now I'm with Enterprise DB, and it's been a real joy doing this. My wife says I can't retire because she's like, what else are you going to do? You're already kind of flying around and visiting places and having a lot of fun. So it is a very unusual job. A lot of people don't really understand what I do because they're like, well, you're home a lot, and then you like disappear to these very far places, and then you come back, and then it's just very odd.
Not a day, not a clock in, clock out kind of job, is it really?
Yeah, I think there's a handful of people that kind of understand. But it took my parents even a while, I think, to get it.
That's brilliant, man. That's really interesting. And with Postgres, then in particular, like as you say, it kind of came about in like the mid. Well, you heard about it in the mid 90s. It was all right to maybe like do a bit of backstory about Postgres, like how it came to being, and like what the other alternatives were. Because I know you said you chose Postgres. Like what was the decisions behind that?
Yeah, that's really interesting. So, I know I started in 96, which sounds like a long time ago, but the code actually goes back 10 years before that, which is, so it's 2016. So Postgres is in its 20th year of open source, but it's in its 30th year from origin. So it was originally developed in 1986 by Michael Stonebreaker, the same person who originally developed Ingress. And it was designed as being basically post-Ingress. So that's why it's called Postgres, because it's post-Ingress. And it was designed to be the next generation of relational system. And the term they came up with was object relational. And the reason it was so groundbreaking at the time is because even until recently, when you had a data type or a stored procedure language or an operator, those were all baked into the database. Like, you had the integer was defined in the binary. A text string was the format for a text string was defined in the binary. And you had really almost no ability to add new data types, to add new operators, to add new stored procedure languages, to add new indexing and so forth. And Postgres in 1986 was designed to allow you to plug in new data types, new languages, new indexing, new operators. There's a whole span of things that you can add to Postgres, new functions, obviously. And that sort of object relational heritage was there when I took over or got involved in 96. And it was a struggle the first couple of years, but now you have a lot of the features of Postgres, which are always taking advantage of that pluggability. So when you add JSON or you add PostGIS, you're really kind of adding them to an existing structure that already is designed to allow for the addition of new data types and new features. And that's some of the things that have allowed it to sort of take on some of these non-relational workloads and some of the interesting workloads that I think we're seeing now that no other database really can take on, relational at least. Like, so we do JSON really well. We do range data types really well. We do GIS really well. We do full text really well. Some relational systems can do some of those, but they usually do it in a very awkward way that's sort of it's not fully functional. Whereas in Postgres, all of those are effectively native, and they appear to be native when you either use them or install them. I didn't realize that in 96 when I chose Postgres. I just chose Postgres because it was closest to the enterprise databases that I had been using in industry. So the transition between Ingress and Postgres, or Informix and Postgres, pretty much the same syntax was understood, the same support was there, the same clauses, the same write-ahead log functionality, the same sort of tuning. It had a very familiar feel to it. And that, of course, has helped a lot of people to migrate to Postgres. In recent years, we've seen huge migrations. We've always had migrations, but the past 3 years or so, you've seen huge organizations now moving away from proprietary databases to Postgres. And I think that's going to continue. And so the familiarity is part of that that it really is designed to be an enterprise database similar to the other ones out there.
Segueing a little bit, but I just been working on a project for the last sort of 6 months, and when I was sort of specking it out, I realized that the amount of volume I was dealing with was a lot higher than any other sort of websites I'd ever worked on. And so basically I went to Ed and I was like, what database should I use? And people told me all sorts, and Ed was saying, well, go with Postgres. And I'd never used it before. And like you say, I guess from my background, using MySQL in the past, making that switch, it wasn't like, a huge move away, although there is, a lot of differences. But one of the things I sort of said to Ed the other day is, do you have a benchmark for how long a query should take? And I mean, you didn't really have an exact answer, but is that something that you yourself have? Will you have like a benchmark? You say, well, if this query is taking this long, then, it's not right. Or how do you really measure what's a good query and what's not?
Yeah, I have a whole bunch of talks basically related to performance tuning and looking at whether the system is tuned properly.
Yeah.
And again, it's almost identical in terms of concepts as the way you would approach an Oracle or an Informix or DB2 sort of performance problem. So the reason there isn't really a benchmark for specific queries is that, and this is one of the reasons that I think the databases are so interesting, is that effectively, unlike most applications, which have a pretty standard API and a pretty standard way of interfacing, a relational database is designed to interpret a language. And in fact, it's a language that's declarative, not imperative. And what I mean by that is that in SQL, you are declaring what you want, and you are asking the server to interpret that and to figure out the fastest way of giving you the result. That's compared to an imperative language where you basically tell the computer what to do. Open this file, search to this index, whatever. You don't do that in SQL. Yeah. So there are many systems that can take, where your average query is defined in terms of milliseconds or even microseconds. Say, all right, the average query time, should be two milliseconds for this class of queries. There are other systems more in the data warehouse space where a query running for several hours would be quite normal.
Yeah.
So what we normally tell people to do is to look at 3 areas of your system. The first is hardware. Database systems are very sensitive to permanent data storage, what we call fsync, or the flushing of your data to some permanent area. And this is what's required for ACID compliance on a relational system. So when you commit a transaction, one of the requirements for an ACID compliant database is that you're guaranteed that even if the server loses power, that data that you committed is permanently stored. So it's basically the D in ACID is durability. And that means that your storage subsystem, particularly your I/O, has to be very well tuned. Normally people, when they select a database server, they focus a lot of times on the CPU, and then secondarily on the memory, and then tertiarily on the storage. Normally for a database server, the storage is the most important part. Then the CPU is actually not that interesting. Most systems in production are running fairly idle CPUs because they're typically bottlenecked on I/O. And if they're not bottlenecked on I/O, they very well could be bottlenecked on the memory bus. So once you have that down, then you start to look at the server configuration parameters. There are a handful or probably dozens of server configuration parameters in Postgres that control performance. There's probably only 3 or 4 that are probably important for an average system. And then once those are handled, then you start to look at the SQL. Do we have the right indexes in place? Are the queries well constructed? Is the data normalized in a way that would give good performance? So, if you're thinking of a very simple type of piece of software where it's just a get and a put, right? Like think of a REST interface or something. Yeah. That's really easy to benchmark. Like, okay, it should take this long to get an answer because I really can only ask one thing, right? Yeah. Problem with Postgres and all the relational systems is that I can ask a whole bunch of things. So you end up looking at things like, your hardware, your server config, and then your queries. And then if you need to benchmark, you probably want to start either something like pgstat statements, which comes with Postgres, or PG Badger, which allows you to look and say, okay, here are my slow queries. So what you can do with those two tools is to effectively run your workload for a couple hours or a day. And what you're doing during that process is either collecting the logs in PG Badger or pgstat statements. And then you can look and you can say, okay, here are my 4 slowest queries. Why is that happening? And then you can kind of drill down. And you can even look and say, well, these queries might not take a long time, but they run so often that effectively, even if a query only takes half a second, if you run it 10,000 times, right, then that might be a query that's taking a lot of time.
It's going to mount up over time.
Mm.
Yeah. And sometimes, sometimes the answer is it's doing as good as it can. But then there are other times when you can, this is the thing that always bothers me. A lot of times there are these unbelievably small changes you can make, which just like rocket your system, like your system just becomes like 10 times faster. And I'll give you a typical example would be, if you're using a database server and every time you're committed to a transaction, we're flushing it to durable storage, but you don't have any like battery-backed memory either on your controller card or on your SSD, and you're flushing these F-syncs to magnetic disk, right? And therefore, you can only F-sync a magnetic disk like 250 times a second. So no matter how fast your server is, you're basically throttling all these clicks to 2x. So that's why I usually look at the hardware first. A lot of times an SSD with a battery, when you put your write-ahead log on there, can give you just unbelievably great performance. Sometimes doubling the amount of memory, because so you're not pulling, you have more stuff in memory. You're not pulling so much from the I/O. That can make a huge difference. Increasing shared buffers can improve things. Increasing a parameter called workmem can reduce the amount of on-disk sorting that we do. So those are kind of the things that I look at. At the SQL level, there isn't a whole lot to break. Obviously, if you're missing an index, it can help. Yeah. But most people kind of have that down. But it is kind of an art. I mean, there's a bunch of books that say sort of the art of, performance tuning or whatever. And it's kind of an art because there isn't really a cookie cutter way of going at it. You have to look at those 3 stacks or those 3 levels of performance and kind of make sure each one is functioning well, from the bottom up. And once you get it there, it pretty much stays there. It doesn't break usually. And there is quite a bit that you can do. But the unfortunate thing is normally you either have to take some class or you have to read, quite a bit about performance tuning to kind of have a sort of an eyeball idea of, oh yeah, this looks good, or oh yeah, this doesn't look good. Another thing I've recommended some people do is, if depending on where you're located, is to just bring in a consultant for a day. It's not that expensive. And just have them look at your system from top down. And usually within a day or two, they can either say, hey, everything looks great, I really can't improve things, or, hey, things are good, but we can make these 2 changes, and I think this is going to make a big difference. And that's a lot of times the most efficient way, particularly for developers who don't want to spend a whole lot of time sort of learning the ins and outs of the system, to just bring somebody in for a day and have them sort of check things out. That's usually pretty economical because there are a lot of Postgres support companies around the world who do that.
I think that's great advice. One thing I was reading yesterday, I've been reading Sam Newman's book on microservices, and there's a bit where he's talking about splitting up schemas. But one of the things he talks about is, I think he mentions Postgres with this, but having was it a replica table? Can't think now. Where you have one which is like just for reading, so that the other one that you're writing to is just freed up for that. Is that something that you recommend as quite an easy way of increasing performance?
Oh yeah, absolutely. So this gets a little philosophical, but what you're really asking about is multi-server database architectures. So obviously, it's great to have everything on one server, but as you know, when you get to certain workloads, it's just not possible anymore. Yeah. Either because the network becomes saturated, or the I/O channel becomes saturated, or the CPUs become saturated, or you just can't stuff any more memory in the system. And once you decide that you want to go to 2 or more servers for your database, you really have a decision to make. The 2 options are that you're going to use the additional servers only to handle read-only traffic. The second option is an option where you say, I want to do read-write traffic on all of those additional servers. The deceptive answer is, I just want the second one, because then I don't have to really think about which server I go to, and everything will be hunky-dory.
Yeah.
The downside, the thing that very few people understand, is that databases are not like web servers. So if you're running a static web server and you need more traffic, you just create new web servers on more machines, and you just copy the www directory over, right?
Yeah.
Load balance across those web servers, and boom, you're 10x or 20x or however many servers you want to add. The reason that works so well is because the web traffic, the web contents being served is static. But by definition, your databases are very not static, they're dynamic, and a lot of them have very high write workloads.
Yeah.
And when you try and spread write workloads across multiple machines, things become very complicated and potentially very slow. Interconnect between those servers, no matter how good it is never going to be as fast. The CPUs are between the cores on the individual CPUs. So when somebody comes to us and say, well, I want to use multiple database servers, and I think I want read-write on all of them, the problem is that when you do a write on one of them, you got to do a write on all of them. So you're really not, you're generating a tremendous amount of delay because you've got to pump all this write traffic to however many additional servers you have, which again doesn't apply to the web server case because you never change anything effectively in a static case. But then once you do that, then you also got synchronization issues. You've got to commit those transactions atomically on the multiple machines. It becomes very complicated. So normally when people come to me and they want to do multiple database servers, I always try and steer them to the case where, as you've alluded to, where I have one write server, but I have multiple read-only servers. Okay, so I have one read-write server and I have multiple read-only servers. And the easy way to do that is effectively to set up streaming replication between the master and all of your read-only servers. Yeah. And you can have dozens or even hundreds of those. You can cascade them. So you can have the master write to 5 read-only servers, and then each of those can serve another 20 or whatever you want to, whatever architecture you want to set up. And what's great about that is that there's no coupling between those read-only servers and the master server in terms of data modification. So you can't write anything to those read-only servers. You can scale them as much as you want. You don't slow down the master server because there's no waiting. There's no sort of pump of write queries that are coming into that thing from these read-only servers. These read-only servers are just doing reads. So that's a very simple architecture. You have to do a little bit of work at the front end. Either you have to use something like PG Pool to send the write queries to the master and then load balance the read-only queries across the other servers. Or if you're doing data warehousing, you probably know you're doing read-only queries, and you just run the data warehouse queries on the read-only servers directly. You don't even bother with load balancing or trying to get the right read to go to the right servers. But that's a very, very popular case. We are working on sort of multi-master sharding, which I think is a case where you have such great data volumes you can't even write them to one server. That's when the master would become overwhelmed. That's sort of a high-end case we're probably a year away or 2 years away from. But I think the simplest answer when you get started is to really go the simple route. Create those streaming replicas. They're very easy to manage. They're very easy to set up. They have almost no overhead on the master. And you can get tremendous read scaling in that case.
I think that sounds really cool. It's definitely something I'm going to do. And I think the other thing Sam Newman said was you could even have it, you can configure it so that if your master does go down, then the writes then happen on the slaves.
Absolutely. So there's a special trigger file that you define when you create the replica. Yeah. And the system will look for the creation of that file. And as soon as that file is created, either by you manually or by a failover mechanism, or some heartbeat program, all of a sudden that replication becomes the new master.
Sure.
That's cool.
So yeah, so you're not only getting read-only scaling, but you're getting high availability as well.
Well, one thing actually, like you spoke about at the beginning, was the fact, that SQL is a declarative language, and as a fact, it's a beautiful thing, really, where it hides a lot of the complexity that we don't really matter. Doesn't really matter. We're just asking for things, and it decides itself the best way of getting those. And a lot of your talk, well, a couple of your talks, sorry, have been like around the optimizer and the query optimization, because what is the best route to get these, to get this information? And obviously what Mickey was saying, with like benchmarks on queries and stuff, it's like, well, Postgres, and all these relational database systems and everything with SQL, really they need to do a lot of things. They can't just specify on one thing. So it's really the fact that it's got to do so many things. How do we choose the best query? And I was just wondering, like, how do we to kind of unwrap the SQL and to work out what's actually happening? What methods do we have for that?
Yeah, so I think that sort of smarts in the database, the optimizer. I think that's sort of one of the sort of unsung heroes of relational systems, because before we've had relational systems for so long that we kind of forget what it was like before. And what it was like before relational systems or before query optimization is that effectively applications had to know how the data was laid out. If they had to know if an index would be useful for a particular constant or value, they had to do the joins inside of the application. So you had to look up the customer record, and then you'd have to then open the order record and then look up all the orders that match that and so forth. And relational systems really took a lot of that problem away, and they took it away in an interesting capability, because not only did they sort of have smarts to figure out what the current layout was, but as the layout changed, as you added new tables, as you added new data, which changed some of the assumptions about how best to return the results, the query optimizer automatically figures that out, because you're regularly generating updated statistics which record what the most current, what the 100 most common values are in Postgres' case, and it also creates a histogram of 100 buckets to know what spans of values are very common. So you have that kind of smarts there, and it really takes a lot of the burden off of the application program. And the applications become very much easier, because the application program can just declare the data they want, and the server will basically go and get it. The easiest way to access what is actually happening inside is to merely prefix the SQL command with the word explain. So you can do explain select, explain update. There's a whole bunch of explain commands. And effectively, when you do use the word explain before the SQL command, you basically get to see the way that the optimizer has decided it's going to go at the data. So you can see what order the tables are joined in. You can see whether indexes are being used and which indexes are being used. And you can even see the types of joins that have been selected, like a hash join or a merge join or nested loop. And you can basically get a feeling for exactly how the optimizer has decided it is going to get at the data. And if you asked the question earlier about performance tuning, I mean, that's one level of performance tuning where you have a query that's running particularly slow, you think it should be much faster, and you run explain on it, and you sort of dive into that explain plan, and you look for either things that are missing. Perhaps there is an assumption about a constant that's incorrect. Perhaps there's a missing index. Perhaps the way the query is phrased is causing the optimizer to do something unusual, and you can change that. So the explain, to me, is really like a window into that optimizer, and it's used very frequently for debugging and performance tuning purposes.
And with this explain, actually, it's really interesting, because obviously when you unlock it and you kind of peek behind the curtain and you see what really is going on. I know from personal experience, you'll start looking at these and you'll look at these little phrases and things, and you'll be thinking, what do these actually mean? Like, it's a whole new world, essentially. The different scan methods, as you mentioned, joins and things like that. And I thought maybe it would be good, if you don't mind, maybe we kind of go through some of these to kind of demystify them a bit, where, at least then where people will understand, like where things, because I'll tell you one story I had was that I used to think that any sequential scan was a bad thing. I used to think if you had a sequential scan, it was a bad thing. So my kind of red herring was, if I didn't explain it was a sequential scan, I'm doing everything possible to not make that. Now, obviously, then listening to your, watching your videos and kind of reading up more about this, I realised actually what exactly a sequential scan is, and kind of more in depth about what's actually happening and why maybe it is actually beneficial. So the first thing I'd like to then discuss is the scan methods, and like what exactly is a scan method?
Yeah, so the terms that we're using here really seem kind of exotic, but the nice thing is that they're pretty common across all of the relational systems. So like the terms we're going to talk about, scan method, join method, and so forth, they're pretty basic. Obviously, the optimizers are significantly different under the covers, but the concepts are pretty much the same. So you're right. As you're looking at it, you're basically saying, okay, I declared I wanted a specific piece of data, and now what explain is doing is it's allowing me to see what the optimizer has decided is the best way to get it. So we're going from declare to imperative, basically. We're seeing the imperative results of the declaration that was in my SQL. So there's three possible scan methods. I do have a nice presentation on my website called Explaining the Postgres Optimizer. The nice thing about that is it has diagrams, because frankly, I've always been frustrated that unless I see a diagram, I can't understand what's going on.
Yeah, and I really enjoyed actually your kind of looking at code of like how this is written in code as well. That really helped me.
Yeah, like the pseudocode in
That's
Perl.
It. Yeah,
was kind of neat. I can usually when I present, I don't get a chance to really go into that because it's really hard to show code a Perl script in in a presentation, but when people look at it later and they can sit and study it, I think it is very helpful. So again, you're kind of mimicking what an application program used to have to do. So a sequential scan is a case where, just as an application program would say, I'm going to open the file, I'm going to read every record from beginning to the end. So sequential obviously suggests that it's going to just read it in sequential order from start to finish. And you're right, it's not always a bad thing, particularly if you don't have much restriction on a field, like if you basically say, give me all the customers who aren't in Alaska, right? How restrictive is that? Probably not very restrictive. So, asking for everybody who isn't in Alaska, you're probably not going to use an index in that case because probably 99% of your customers are not in Alaska. And you may want to, for example, you may want to say, give me every customer who isn't in Alaska or Hawaii, right? So continental U.S. maybe. That would be an obvious case where we wouldn't use an index and you wouldn't want to try and use an index. A sequential scan is unbelievably fast. Obviously, it's reading sequentially, so it uses the read ahead of the system. It doesn't have to bounce around to the index. There's no random I/O going on. So that performs really, really well when you're really going to look at the bulk of your data. The second method is an index scan. That would be a case where you're looking at a secondary index, looking up specific values that match a certain restriction, like, customer is in Illinois, or, customer name, is a specific string. Those would be cases where you're going to be looking in an index, typically a B tree, although we do support a number of non-traditional indexing methods, particularly for non-relational data like JSON and full text search and so forth. We have gin and dist for those, but just the simple case would be a B tree lookup, looking for a match of a name or looking for a match of an ID. You're going to go to the index. It's probably going to pull one or two or maybe more matching rows. And then we're going to go to the heap, which is where our sequential data is, and we're going to just pull the records that match. So those are probably the two completely opposite options for an access method. The third one is kind of in the middle. It's what's called a bitmap scan, and this is a really creative solution where you've got a case not like sequential scan where you're really going to go at the whole table or the majority of the table, but not as restrictive as an index scan. So you're not going at Alaska. Maybe you're going at, give me all the customers in, several U.S. states maybe, okay? And what a bitmap scan does is it basically goes to the index, it finds a bunch of matches, and typically for a bitmap scan, you may have dozens of matches, maybe even hundreds for a very large table, and then create a bitmap of all of the matching possible records. And then once you created that bitmap, maybe for one index, maybe for multiple indexes, you can actually create a bitmap by joining multiple indexes together. So if I was to say, give me all the customers who are, in Arizona, who, also owe us money and, get UPS shipping, for example, that may require the access of 3 different indexes. And what we can do is we can access all 3 of those indexes. We can create a bitmap in memory that represents the union of all of those requirements together, or potentially or if you're doing multiple different states, you have or clause, you can do the same thing. And then once you've finished with the bitmap, you can then access the heap data in a much more efficient manner. So that's sort of a hybrid between the two. You don't see that implemented in all database systems, but Postgres has had it for a number of years. And it's particularly useful for data warehousing, where you've got like indexes on everything, and you have this incredibly complicated query, and you want to basically take a bunch of indexes and merge them together. That's also a great use for that bitmap index scan. And you do see explained reporting a bitmap index scan for cases that are not as restrictive as an index scan, but not as wide open as something that would require a sequential scan.
That's really cool. And actually, the talk that you mentioned, the optimizer talk, it had a really cool example using the rel name table, the PG class rel name table.
Yeah.
And I really, really enjoyed that. And it highlighted, and I say, I recommend, I'll put it in the show notes to everyone to check that out, because it really showed. And I was just wondering, so you've got these 3 different types of scan, and then the explain comes along and it's saying, oh, by the way, here's the cost and here's how many rows and things. Just wondering, what actually is the cost then, and the size and all these? Because obviously I think that, Postgres has obviously got to decide on, it's got many paths. It's got, all these different routes it could choose. How does it go about, based on the heuristics, based on the scanning, which one to choose?
Yeah, I always cover that. So cost numbers themselves are meaningless. Well, let me say they're meaningless in relation to the real world. So I think the cost number represents, I think it's the sequential access of one page. I think that's what the number means. And all the costs related to CPU cost and random cost, all kind of wrap around those individual numbers, okay? But the cost itself is kind of like it's sort of a made-up, a pseudo number. And the only reason it's important is to compare against other numbers. So you don't really care what the number is. As long as this plan is cheaper than that plan, that's what we're going to go with. So the number doesn't mean a whole lot. You can't really relate it to anything. It's not related to milliseconds or anything like that.
It's just related to itself, like to others.
So it's just related to itself. The other weird thing is the numbers are never accurate 100%. You have to walk in accepting that the cost numbers are never going to be 100% accurate, particularly because when we collect statistics, we only randomly sample the table. So we're probably only looking at 1% of the rows when we do a random sample of a table. Because
so when you say random sample, you mean that that's happening every so often? It's getting heuristics to decide, okay, this is information that we now know. Oh, by the way, they're very common. This looks very common. This is very common, and it weighs out those routes decisions.
Exactly. So when you have a command called analyze, which allows you to manually generate those statistics if you wish, particularly if you populate a brand new table, you may just want to run an analyze just to get some stats on it. And the analyze typically takes 20 seconds. It's really fast. It's usually less than 20 seconds. It's just going to randomly sample the table and pull out your data. Now, if you don't do that, if you don't run analyze, there is an auto vacuum system that's been in Postgres for years, which will every minute it wakes up and it looks at all the tables. And it looks to see tables that either have no statistics or tables that have old statistics. And what it will do is it'll basically, in the background, run this analyze command for you. So most systems never need to run analyze because effectively it's being run for them in a helper process anyway. But the other sort of aspect of this is that even if we got full statistics at a particular time, right? As soon as somebody does an insert, delete, or an update, the statistics are invalid because you're going to be changing your data. I mean, if you're not going to change your data, why do you need a database? Right? So we know that those statistics are going to change. We could go nuts and just reanalyze every time somebody does an insert or a delete. But there's no reason to do that, because the numbers so the auto vacuum system, I think every time, I want to say like 10% or 20% of the table changes, the system will automatically run this auto vacuum again, because it thinks the statistics are stale, meaning they're not fresh anymore. But the bottom line is that if the statistics are inaccurate, which they always are, they don't have to be completely accurate, because all they need to do is compare against some other plan. So typically when you run an explain, you're going to get an explain plan with a bunch of costs and whatever. Odds are the next possible plan was like 3 times as expensive. So who cares if we didn't get accurate statistics? We were good enough that we didn't choose this super bad plan, right? And effectively we got what we wanted. The other problem is, even once you start to do over 12 tables, we randomly start checking plans. So if you try and do a join with more than 12 tables, we have something called a genetic query optimizer, and it will randomly try different paths, because effectively, if I take an hour to optimize a query that takes 5 minutes, well, that's kind of stupid, right?
It's an hour and 5 minutes for just something
else.
else.
Why don't you just run a lousy plan? It would have taken 15 minutes, and we'd be happy, right? So you always have that tension between the time and the cost of getting the best plan versus the amount of time it takes if you choose a suboptimal plan. Because in a lot of cases, a suboptimal plan is not that much worse than the best plan you could possibly do. And this is a problem that every relational system has. I think Postgres has been fortunate because we have such a very close relationship with our users, and because we get very good bug reports and we work with people within 24 hours, we typically can nail down and optimize their problem and typically give them a patch that they can test to see if it fixes the problem. That we've been able, obviously, from the optimizer we inherited in 1996, to develop, pretty much, if not the best of breed, certainly one of the best of breed relational optimizers out there. And it does a lot of really cool stuff. And it's very well tuned. And if something's wrong, we hear about it from our users, and we dig into it and we find a way to improve it. And that's in contrast to a commercial or proprietary database, where the process of actually reporting an optimizer bug and getting to the engineers and having those engineers communicate with the users is this incredibly long, frustrating process. And because we're open source, and because our developers and our users and our designers are kind of all the same people, we're able to kind of short circuit that. And because we're open source, we can release really quickly and get patches to people and help them to try it out. So it's kind of an area that I think it's fascinating. It's one of the optimizers, one of the reasons I got involved with Postgres. Tom Lane, I know, also was curious about the optimizer, what got him excited in getting involved. But again, most people don't really even know it's there, and they don't really have to, because it pretty much does.
It's almost too good, isn't it? As you say, well, not probably isn't too. It's not bad that it's too good, but it's the fact that because it's so good, people don't need to worry about it, because it's going to be doing most, the right thing at the, for what you need.
Yeah, I did work in the 90s with some relational systems, which I won't name, which were much less good than what we have now. And I do know that it was very, very frustrating to report a problem. And a lot of times this resulted not in slow queries, but queries that returned incorrect results, which is obviously super serious. Yeah, and it was just a very, just a very frustrating process.
You mentioned the indexes, where you can do an index scan, and I think a lot of people, when they look into like look into the database relational world, and they kind of look at performance, they'll look at explain, they'll be like, oh, you need to add indexes, and it's good indexing, and I'm just wondering, like, because Postgres has a very rich indexing system compared to some other, other relational databases, and the ability to do partials and expression indexes and different types of indexes, many to one. I'm just wondering, like, is there like a kind of general consensus of like which one's best to use, or is it very much specific on the data that you're doing it on and things like that?
Indexes are kind of how do I explain it? It's it's deceptive. People a lot of times will add an index and they'll say, oh, okay, I'm doing a sequential scan. Let me add an index. Oh, great, this query now uses an index. My job is done, right? But the thing that they don't understand is that the index is very often going to have overhead. So when you create an index, what that means is that every time you do an insert, an update often, or a delete, you've got to touch that index. So what happens is a lot of people looking at a single query are saying, oh, wow, okay, this query became a little faster by adding an index. What they don't understand is that all of the other inserts, update, deletes that are happening in the system now have more work to do. And what's deceptive about it is the cost of those inserts becoming slightly slower is very rarely calculated, because there's normally a very small number of milliseconds that it takes to add that. But if you're doing a lot of activity, it's very possible for that index actually to be a negative. Particularly if you add an index really for a query you're only running like once or twice a day. Okay, you see that a lot in data warehouse when you're trying to add a data warehouse query to an existing system, and you say, oh wow, okay, this I can cut 10 minutes off if I add this index, but you're probably lost more than 10 minutes during the day if that table is heavily modified. So there are a bunch of different index types in Postgres. As I mentioned, B-tree. There's also gist. There's also gin. And those are designed particularly for non-relational cases where you have a lot of duplicates in your data, or you've got a piece of data that has like an X and a Y component, like a geometric, where you're actually, you have to index both points at the same time. You can't just index the X and then look up the Y. You've got to have what is called an R-tree index, which actually uses bounding boxes to record sort of what pieces are in which parts of the graph or which parts of the geometric space. And that's kind of, that's sort of a different type index. I think Postgres does really well with that kind of spatial stuff and that sort of non-relational stuff. In fact, I have a non-relational talk on my website that goes over 8 very popular non-relational areas. And what's really cool about that is you have unique indexing specifically designed for those non-relational data stores.
That's so cool. As you say, you've got the scanning, down, and you're able to work out and look at your indexing and things like that. And then you'll look, we kind of spoke a little bit about the joins. And then there are like the 3 main joins as well. Sure.
So, and again, these are traditional to all relational systems. So Postgres implements them, but you see these in different other relational systems as well. So the simplest one is what we call a nested loop. And that's just basically take every row and compare it to every other row, right? I mean, that's the way if an application has to do a join, that's typically the way it does
it. The naive way of doing it would be,
it's just like I is 1 to 10, J is 1 to 20, get nested inside of it and just loop through either one, right? That works fine if you have a small amount of data. But if you got a lot of data, if you have 1 million rows in each table and you try and do that, you're talking 1 trillion comparisons, right? Because it's 1 million times 1 million. And 1 million rows is not that many, right? So you just can't do a nested loop for every case. The next one, which is a little more interesting, is instead on the inner side, which we would typically do a scan on the inner side. What we do is we create a hash. So we take one of the tables, we hash it, and then we do lookups into the hash. So instead of having to spin through all 1 million rows on the inside, we basically hash the 1 million rows into buckets, maybe 1,000 buckets. And therefore, if I'm looking for a particular row, I just look at the bucket that matches that particular hash key I'm looking at that hashes to that match, and then maybe I look at 3 rows. And that obviously is a little more sophisticated, probably not something you're going to do in an application, but you could. But again, it's done automatically for Postgres for you. And Postgres automatically will choose either a nested loop or a hash automatically, depending on the sizes of the table as is recorded in the table statistics. The third one is a merge join. This is the one that's probably the least intuitive. And in this case, you end up sorting the 2 tables. That's quite expensive because you got to sort both sides. It's kind of a bummer. But what's great is once you've sorted both sides, you can basically compare the first row to the first row. And if that matches, you can try the first row to the second row. If that matches, the first row to the third row. If that doesn't match, you know there are no further matches in that table because you sorted the inner side completely. Because if there was a match, it would be there. So then you can go to the second row in the outer side. You don't have to start at the beginning anymore because you know that the data is ordered and you know there are no rows before where you stop. And you can just compare. As soon as there's not a match, you can go to the third row and do the same thing. So you basically end up doing a lockstep walk through the two tables, and you effectively are only really sequential scanning once of each side. So you go from the top of the first table, of the outer side, the top of the inner side, and you basically walk down in a synchronized manner. And when you get to the bottom of both tables, you're done. And that's not intuitive, but of course is very traditional for relational systems. And Postgres Optimizer is obviously smart enough to know, I want to use a nested loop here because the tables are small. I want to use a hash here because the tables are medium. Or, these tables are huge. I better do a merge join.
And how intertwined then are these decisions? Like, the scan that it will use compared to the join it will use, the joint ordering. Are they all kind of weighed up together?
Yeah, so the way the system actually goes at it is it's got weights for a sequential scan. It's got weights for an index scan. It's got weights or costs for a bitmap scan. And then it also has cost of how expensive an index, a nested loop would be, how expensive a merge join would be, how expensive a hash join would be. And it basically just tries them all. So it says, here, I've got two tables. I can use 5 indexes potentially on each table. Let me try every table with all 5 indexes and all the 5 join methods and see which one is cheaper. And then once it picks the cheaper one, it basically is done joining those two tables, and it just keeps the cheapest one and then moves on to the third table and fourth table and so forth. So it really is all intertwined with the cost system. Not only is the cost determining scan method, but it also has pre-built costs of how expensive a nested loop would be. So for example, a nested loop on a small table is very ideal because there's no cost. You don't have to sort anything. You don't have to hash anything, right?
There's no boot up, no pre-step at all.
Right. You have two. This is what we call the startup cost. So you have 2 tables. Each one has 5 rows. Well, it's 25 comparisons, right? That's going to be like a no-brainer. That's going to be nested loop. However, if there's, let's say, 10,000 rows in each table, right? I might want to do hash join because I can hash 10,000 values really fast. I can't do a nest. The cost, when I compute the cost of 2 10,000 row tables in a nested loop, it's going to be like, what is that? Like a trillion or something? A billion. It's going to be a billion. It's not good, right? So what we're going to do is we're going to look at how expensive is it to hash something, and we have costs exactly, per row. What's the cost of hashing 2 tables together? And we can cost that based on the number of rows. And then if there's obviously a really big number of rows, then we're going to have to do a merge join, and we're going to have to do thousands of comparisons. So again, it looks at the cost, it kind of computes what they end up being, and then it figures out kind of what the result would be.
Mickey, have you got any other questions?
No, I think you've covered it all. It's been really interesting.
Yeah, kind of a whirlwind tour over all the performance stuff. I think it's really interesting. I think it's these kind of areas that, particularly like for me, I'm very interested at the moment with like the SQL and how the query optimizer works under the hood, because it's that kind of black, like that, that black box kind of feel to it, when you first look at it, where you just look at the declarative, and it's just working, and, but it's like, well, why is it actually working? So it's really interesting to learn these terms. And I really appreciate it, Bruce, you coming on the show to explain this, and I'll put all that in the show notes, all your links to your videos and stuff, because they are just an amazing resource.
Great, yeah. It's what's always kind of interested me is this kind of detail of how everything works, and how it works inside. Actually, was always kind of fascinated me. Like it appears as magic, but then when you understand how it all fits together, it's understandable.
That's it. There is no magic. You're going to uncover the magic. Yeah. No, again, thank you so much, Bruce. I really appreciate it, and I know it's been a bit of a manic time trying to get this organised, but I'm really glad we were able to have this good chat.
Yeah, my pleasure.
Awesome. All right then, audience. Well, it's been another great episode, and we'll speak to you again next week. Goodbye.
Thanks. Bye.
You've been listening to 3 Devs and a Maybe. You can contact us at contact@3devsandamaybe.com or follow us on Twitter @3 Devs and a Maybe.